else.
How many people are sleeping cheap at this point?
Sorry, what?
How many people are sleeping?
3.
Oh, no, it's okay. You're already.
Yeah,
I think I forgot to.
Nanda will come for sure. Yeah, I'm not sure about other guys. Let's just wait for 2 more minutes and then let's start.
Thanks for getting everything over.
That's okay. Like, yeah, pizza is it's never, over the limit, I guess. Yeah.
Did you actually get all the pizza by yourself?
Oh yeah, it's okay. I took 52, so I didn't have to work all the way like
Carry all
you.
6 of them?
What?
Carry all 6 of them?
Yeah.
It's terrible.
So it's okay. No, it's just fun. Like I think like picking up the coffee is more difficult, I guess.
Is it?
You have to walk the long way up, like uphill.
I suppose.
Yeah.
Do you get up from Pete's Coffee like on
Yeah.
south side?
On the north side.
Oh.
Yeah, maybe next time we can try the south side and we can
Well-
take the reverse.
Honestly, north side might have a better bus route. I just didn't check. South side doesn't have a bus route, I guess.
Oh no, if you order the coffee from the Pete's Coffee near the crossroads, there's a reverse line. Even though
is
that,
it?
yeah, even
Mm.
that can take a long time. Maybe 15 minutes
Yeah.
one.
Yeah.
The interval is 15 minutes, so yeah.
It's only like a 20-minute walk. It's not that bad.
Okay. Good.
I'm sure if Nanda is going to join us.
Hey, what? Great. Yes, in the yard.
Okay.
Lots of. Yeah, I don't know. Yeah. What? Oh, that's a Discord channel. Yeah, but then I'm looking. Subscribe to the latest updates. Oh,
We have a
are you
We?
emails? I don't think so. Oh, man, yeah, let's see.
Hold on.
No, not Discord.
How can I?
He's scanning this one. Wait, let's scan. Oh.
Display
It's
set.
not equal. They're doing emails. Oh, it says. There's some I feel this before. The never seen.
Hold on 1 second. How can I share?
Add your.
I think I should be able to share
Yeah, I'll add your.
Yeah, if you-
the entire screen. How can I make sure?
If you share PowerPoint, it should configure it properly.
Oh, that's yeah. I think it's great.
So if you share PowerPoint and now go into presentation mode.
Yeah. Right. Okay, let's start. Nice.
Yeah.
So I guess I'm.
So it should be recording that one
Yeah. Right.
up there.
Right. So thank you for coming. And today I'm going to talk about my research regarding stress intensity factor-driven phase field modeling of mixed-mode fracture. And I guess I will split this presentation into 2 parts. The first part I will talk about my research, and second part I will talk a little bit about how to use Phoenix, because I feel like most of us are using finite element method in our research, and Phoenix is a really great open source package, and it has a really great Python interface. So basically, you can use that to model your just build up your model in finite element method. So I will start talking about my work first. So I will start talking about the motivation of my work. So this is so what is phase field method and what is conventional phase field method? Basically the phase field method means that you convert a discontinuous singular crack as shown here in the dark blue into a smear field around it. And by doing so, you actually have a field in the domain, and that would be more applicable for computer to solve it. And in order to do so, you need to include a second partial differential equation to control the cracking phase field. Yeah. And also you need to modify the mechanical field, basically the linear momentum balance equation in phase field. by introducing a degradation function, for example, GD here. And here I use a 1 minus phi squared. This is a very classical degradation function in phase field. And because of the introduction of this degradation function, it has some problem for fracturing modeling. As we can see on the bottom side, we have a square plate with an edge notch, and then it is subjected to mode 1 loading. And the typical stress distribution should look like this in the middle. But if you extract the stress field on the circle, and if you extract the result from the phase field phase field modeling, you will see the stress distribution doesn't align with the classical linear elastic fracture mechanics solution. And the reason is because the introduction of the degradation function GD. Even though when you calculate the stress sigma, you don't explicitly include that 1 minus phi squared, this degradation function, but the existence of this function in the governing equation will generally destroy the asymptotic stress field ahead of the crack tip. And that's why you have a stress field that is very different from the analytical solution. And this can cause a problem because if the stress is incorrect, that means the strain energy density ahead of the crack tip may also be inaccurate. And strain energy density is closely related to the driving force in cracking phase field, as I noted there. And if you have an incorrect driving force, you may have a inaccurate propagation or initiation of cracks of cracking phase field in the field, and that inversely will affect the mechanical field even more. So what I mean is just like the non-physical stress distribution ahead of the crack tip will affect many aspects in phase field method. And this is not the only problem conventional phase field has. So usually the conventional phase field method uses the strain energy density or some certain part of strain energy density. On the right side is a spectrum decomposition of strain energy density. And if you use and usually the conventional phase field method assumes that you use the strain energy density as the driving force to drive the development of the cracking. And that means the crack will propagate along the direction that has a maximum strain energy density. And that part, once that part is destroyed, those strain energy density will be dissipated. And that corresponds to the minimum strain energy density theory. And according to Bajan, in his book, minimum strain energy density criteria does not appear to rest a sound foundation in the thermal mechanics of solids. And actually, if we look at some classical fracture mechanics books, this is a one sentence I quoted. I refer from Ritchie's book, which is said by Drucker and Rice. It says the fracture mechanics is a judicious interpretation of crack tip singular fields. And once we can interpret the singular field ahead of a crack tip correctly, we can have a better model to simulate the fracturing behavior of materials. So my work starts with the asymptotic stress field ahead of the crack tip. Instead of looking at the stress components in Cartesian coordinate, I look at them in a polar coordinate. So then we have three components: sigma theta theta, sigma theta r, and sigma rr. And there are three observations. Actually, the first one is not one observation, it is a conclusion in linear elastic fracture mechanics. That is the energy release rate. Fracture energy release rate G is linearly related to the square of stress intensity factor K1 plus the stress intensity factor K2. So if we can model K1 square and K2 square correctly, we are able to calculate the strain energy density ahead of the crack tip. And how can we do that? by observing these three equations, we will realize that k1 squared plus k2 squared is proportional to sigma theta theta squared plus sigma theta r squared with a factor of 2 pi r. And actually, the crack will propagate along the direction that will maximize the fracture energy release rate. And actually, this is not the finding in my research. It has already been found by previous researchers that and they proposed the maximum energy release rate criterion, or another name is maximum circumferential stress criterion, which means that you can basically link the fracture energy release rate with a sigma theta theta and sigma theta r. And so now the question is, how can we bridge the gap between the classical linear elastic fracture mechanics theory with phase field theory? Because well, we want to make the phase field model more has a solid foundation in fracturing mechanics. And actually, this big challenge can be decomposed into three parts. The first one is, how can we measure the distance from the crack tip to an arbitrary point near the crack tip? Because as we can see in the fracturing criteria, r is always the distance r is always a very important factor in fracturing criteria. So we need to model it correctly. And so this is the first question: how can we measure the distance r? And second question is, how can we convert the stress components in a global coordinates sigma theta, sigma xx, sigma yy, and sigma xy to sigma theta theta, sigma theta r, and sigma rr? Because sometimes we can have a left hand coordinate xy or right hand coordinate xy. And how can we convert it universally to sigma theta theta, sigma rr? This is another question. And third question is, how can we find the direction that can maximize the fracture energy release rate? So the solution in my research is to use the properties of cracking phase field. As we know, it is a field over the domain. And if we look at it in a one-dimensional case as shown here, we can see that the distance can be approximated by the value of the cracking phase field. That means if the distance r is equal to minus L0, L0 is a characteristic length in phase field method, multiplied by log phi. So this can help us to this can also help us in 2D and 3D setting to measure the distance from a certain point to the crack tip, or at least to the notch or to the predefined crack. And actually we can do, and log phi is not very friendly, and we can do Taylor expansion on it, make it two, and we just preserve the first two components as an approximation to the distance. And how can we convert the global sigma xx, sigma yy, those components into sigma rr, sigma theta theta? First of all, we need to find the direction of r. Once we can find the direction of r, we can find the direction of theta, and then all other things can be solved. So how can we find the direction of r? We are going to use the gradient of the phase field. So basically, we know the phase field will smear from the center to its surrounding. So that means if we can calculate the gradient at a certain point, we can find the unit direction for unit vector for r. And in that case, we can eventually convert the stress components into polar coordinates and write them as sigma rr, sigma theta r, and sigma theta theta. So by using the properties of the cracking phase field, basically the value of phase field and the gradient of phase field, we can eventually convert this criterion into a way that is compatible with the traditional phase field method. So here we can see r is replaced by L0 multiplied by a term that resembles log phi. And here we also notice we initially have sigma theta theta and sigma theta r, these two terms. But here we only preserve the sigma theta theta because we are going to calculate the driving force. Oh yeah, you cannot see my mouse here. How can I do that? Later point, yes. Right. Yeah. So here we have so basically we are going to evaluate the driving force all in the whole phase field domain, and that is not something what we want. We want the driving force to be concentrated on the direction where the crack should happen. And by doing, and in this case, we just neglected the sigma theta r, this direction. That means except the direction which corresponds to the crack propagation direction, all other directions, the driving force will be much, much smaller. And we use this way to penalize other directions that doesn't correspond to the principal direction of sigma theta theta. And in doing so, eventually we propose a new governing equation for cracking phase field method. It writes like this one. And now we have already got a very a driving force that has a solid foundation in linear elastic fractional mechanics. But the problem is still that one. But problem is still this, like, how can we make sure the stress are accurate ahead of the crack tip? So instead of using the degradation function here, in traditional phase field method, we adopted the idea of change of configuration. That means we don't have a degradation function here. Instead, we divide the whole domain into two parts. One is omega 0, which corresponds to the domain that has a phase field value greater than 0 and smaller than a critical phi. So this domain we will assume is just a sound material without any fracturing or cracking problem. And then we have another domain that is a phi greater than phi the critical value. So this domain we will treat it as a cracking area or just a crack in the space. So in doing so, we just solve this linear momentum balance equation in sigma 0 domain, and we don't do that in omega 1 domain. And this can be done by Phoenix. And then for the phase field method, we solve it in the whole domain. So the whole domain refers to the union of omega 0 and omega 1. So basically that's pretty much I want to cover. And now I want to show some numerical examples to validate our method and see the application of our method. And you can find my code in my GitHub repository, and feel free to download and use it, and let me know if you have any questions. So first of all, we validate this classical problem, which is a plate with a edge notch under stretch. This is an under mode 1 stretch. And by doing so, we prescribe the mode 1 boundary condition on all the boundaries of this plate, and we specify the Young's modulus and Poisson's ratio and critical energy release rate. And those parameters are given here. And we also use the 3 different mesh size. Basically, we have a coarse mesh, medium mesh, and fine mesh. And then by using our method, we can see the stress distribution is look like this. And if we extract the stress on the circle ahead of the crack tip, we can see the numerical results from the stress intensity factor driven phase field method aligns very well with the analytical solution, which is much better than the conventional phase field method. This is true for all the stress components. And if we look at the overall response of this model, we'll see we can capture the critical cracking much accurately than the traditional phase field method. Here, these three lines, if I'm not sure if you can see, these are three lines here. So these three lines correspond to the result from our model, and this curve corresponds to the result from the conventional phase field method, and you can see a clear stiffness degradation here. It is because of the introduction of the 1 minus phi squared, that degradation function in the linear momentum balance equation. Yeah, so this is a first example to see how our to validate our model, and we continue our journey by looking at the mode 2 loading. So basically, we just specify the mode 2 loading on the boundaries of this plate. We use the same material properties as we used in previous research, and we can see still the stress field ahead of the crack tip, the so-called asymptotic stress field, align very well with the analytical solution. And yeah, these are the distribution of the stress over the domain, and we can see the crack also propagate. The predicted point is also very close to the analytical solution, which is much better than the conventional phase field method. And we can see here, we will observe like 70-degree cracking propagation from the crack tip. And this aligns with the analytical solution. If you look at the maximum circumferential stress principle, and if you look at the solution of it under mode 2 loading, you will see the analytical solution is also about 70 degrees or 67 degrees. So this validates the applicability of our model in both mode 1 and mode 2 loading. And now we want to see how it can be applied in some engineering problems. Here we have a concrete beam with a notch in the middle. And actually, you can see the loading condition is very asymmetric. And we have a concentrated loading on the right side. And on the left side, we have a spring. And the stiffness of the spring can change from 0 to infinity. When the stiffness of the spring becomes 0, that means there's no spring at all, and this is basically a free end. So you can just imagine it as a beam under one concentrated load, and naturally the crack will propagate in a smaller angle. And when the stiffness is very big, for example, when the stiffness is almost infinity, that means this point cannot move at all. So basically that means we have another loading here, and basically this beam is under 2-point loading, and you can expect the crack will propagate in a more inclined way. And those behaviors can be captured by our model. So this gray area represents the experimental data, and we can see the crack propagated by our stress intensity factor driven phase field method is very close to this experimental observation, and also the overall response of the beam is also matches with the experimental data. And when we have a stress intensity, when we have the stiffness being infinite, we can see this is also the experimental data. This is a region where the crack is observed in experiments, and we can see the crack can also be observed in this area. The phase field, the cracking phase field is also able to capture the propagation. So basically that means we can use one method to simulate different mixed mode formulation without any modification. So this demonstrates the applicability of our model in a very general sense. And this is also the overall response predicted by my model, by our model, and compared with the experimental data. And in the last example, this is a very classical problem, I think, in rock mechanics, where a gypsum specimen with a center flaw is compressed. And actually, there are many study observations on it. So basically, those red line corresponds to the primary cracks on the domain, and we can see the crack will propagate almost perpendicular to the notch and then change its direction to vertical. So this is what we can observe in the experiment. And this observation, this phenomenon can also be captured by our method. So we have a predefined notch here, and then we allow the crack. We just implement the SIF phase field method, and we can see at the beginning, the crack will propagate in a 90-degree, in a direction perpendicular to this notch, and then eventually you will generally change its direction to a vertical direction. So this is very similar to what we observed in the experiments. Okay, so basically that's what I want to talk about my research. So there are some key contributions of this work. The first one is the accurate representation of the stress ahead of the crack tip. And secondly, we can precisely predict the crack growth and material failure without any additional splitting techniques, which is widely used in conventional phase field method. And most importantly, by introducing a new driving force, we bridge the gap between the phase field formulation and the well-established linear elastic fracture mechanics theory. So this is the end of my presentation. Any questions? Yeah.
How precise of your methods can apply for, like, how about dimension of the crack? For very small crack, can you return by using this method?
You mean the size of crack?
Yeah. Like for example, in structures, like in the beam, this is last crack, right? So your method can determine that. How about in the case it's very small?
In a very small way.
Very
So I guess that depends on the resolution of your model. That depends on how fine you model you have how fine the mesh is in your model. So yeah, actually, I think this is more relevant to your question. So basically, we have three different meshes. So that means if you have a really fine mesh, you can have a really thin crack, and actually the mesh sensitivity is not a problem in my method because I use the three different meshes and they give me the same results.
Why the picture in the middle has the huge difference between the red line and the blue line?
Red line and blue line.
It's like almost all of the same trend, right?
This red line is the results predicted by the conventional phase field method because, as I said before, they use a degradation function in calculating the stress field. So that's why it deviates greatly from the analytical solution. I'm not sure if you can see it clearly. Actually, there's a black line here which corresponds to the analytical solution, and we can see, yeah, our result is closer to that line. Yes.
So in the third example, you show maybe the last one. No, one of the
This one?
no.
This one?
You can go forward. This one. So
Okay.
you can see in the experiment data, there's some drop in the displacement after reaching the peak.
Yes.
Yeah, which isn't show your numerical solution. So what's the reason that you have a
Yeah.
drop in the displacement here?
From the theory perspective, it is because we use a linear elastic fracture mechanics theory, so it's just going up and drop down. It doesn't have any cohesive behavior. So I think this post-peak branch that corresponds to the cohesive behavior in the material. And I guess this part hasn't been investigated in my research. And another reason is because I observed that the crack can propagate really quickly in phase field method if you don't have any cohesive behavior introduced. or so this is why there's a sudden drop from the top to the bottom. Yeah, I think how to incorporate the cohesive behavior after the initiation of crack is an interesting topic to explore. Yes.
Can you go to the last slide? You see that the tensile is there, and then there is a shear fractures.
Yes.
Right?
Yeah.
Why you don't have shear fracture in your next one?
Yeah. So, yeah, I'm not sure. Well, my theory is because this shear fracture actually corresponds to a domain. It corresponds to one area that's being kind of totally damaged. So it's not like a very clear fracture line there. It's just very so many tiny fracture lines, crack lines here. So I guess that's yeah.
Have you seen there's my friend actually has this. His name is Ian Xuan Hu. He was a postdoc before with Steve's son. I can give you the paper now. Can do that.
Yeah, I think someone also did that using the so-called dual phase field method. Yeah. Yeah, he used a dual phase. I read that paper. So basically, he has two different criteria for two different phenomena. Yeah, for both.
You have one.
So yeah, I just want to use one theory to explain as much as possible. So yeah, I'm also interested in why we don't have this point. Maybe it's because I don't know some flaws that inherently have here or here. I'm not sure if yeah. I guess I need to investigate this problem later.
I mean, to what my discussion with him is that you cannot get this double mode if you do not represent the fracture energy release or release the fracture you have to decompose them. One part is I think that's what he did, right? This double
Yeah.
So one is if he said if you don't do that, you will not be able to get
the double lines. Yeah, that's true. When I did the
because one is going to be dominating the other one, right? It's just either the K1 or the K2. If you pick one, you just in the.
That is so true. That is so true. Yeah.
If it's the weaker, then you just follow that one, and there is no way that you can get the other two.
Yeah, I guess yeah. This makes sense because I just use one GC here as a control parameter. Yeah, that's a good point. Okay, so that's the end of this part, and then yeah, I guess I just want to show briefly about how to use like my way to use Phoenix.
Yeah, you might be able to share.
Oh, okay. Full screen. Okay. So my way to use Phoenix. Well, if you have a Ubuntu or Linux system, you don't have to look at this part. Just in case you don't have one, and I think the best way to use Ubuntu and Phoenix in Windows system is through the VS Code, and that in that case you need to install the Linux system. It's called WSL. Yeah. So first of all, you need to install the WSL in your Windows system, and that you can find, and with that you can find so many tutorials online, like how to activate WSL in Windows. Yeah, so you can just follow those command lines one by one, and then you can install it. And after install it, you can connect to WSL in VS Code. So you can just type in connect to WSL, and then you will connect to it in second. And after that, you will have a terminal here. You just click on this cross and warnings, and then you can just switch to terminal here. And once you switch to terminal, you can, because I install the Copilot, so maybe that's the reason. And then you can just follow the instruction given by Phoenix project. And it writes very clearly. So first of all, you need to install the conda on your Linux system, and then you can do conda create an environment with a name like Phoenix X environment. And it can take some time, and then you can activate it and install all those packages. And one more package I would recommend is a Mesh.io. So I think you can install after installing this one, you can install one Mesh.io, and that will be very helpful for visualization. Okay, so conda activate Phoenix environment, and then you can do conda install. Really need to. So basically, after this, you can correctly install the conda in a WSL environment, and then you can just run your Phoenix code there. Yeah, I guess that's all the thing I want to cover today. And yeah, let me know if you have any questions. If not, maybe we can start our coffee hours.
So for WXL, do you know that whether your memory is are you running still your PC or do you connect to a certain?
Yeah, I'm running on my PC. So
So that
the
means your memory is actually split, right?
uh
You cannot use the full memory.
yeah, I think so. Yeah, you can only use part of it. But I think it's great to run some demos and do the debug work on your computer before running it in a cluster. Yes,
Do you run your stuff single threaded or multi-threaded?
a multi-thread. Yeah.
You direct just call like Python, whatever Phoenix direct to English.
Yeah. So basically, because I use that in Jupyter Notebook, so I just click on run, and basically it will be paralleled automatically.
Oh,
But do you know whether that's actually distributed parallel or is it like
It uses MPI for Pi.
oh I mean,
Yeah,
it's pitch. So
yeah, and pitch. So that's why.
it would be,
yeah.
Yeah. So
that's why you gotta do all the code splitting and
yeah, exactly. That's why you can see so many ghost lifting code in PyC, which is also used by Phoenix. Okay. So if not, I'm going to end today's can I stop the recording? Wait, I found it.